And in fact, we already see signs in our civilization of our civilization heading towards becoming less visible or perhaps even invisible. That our longevity as a detectable civilization may end much sooner than we expected. For example, this is really scary to people like me. What is this? You've all used it, you just didn't know it. This is a synchronous satellite which is used to transmit television programs to Earth. It's used for DirecTV, Dish Network. It's used for the old large dishes. It's actually used these days to transmit even cell phone messages to and from the Earth. And why is this bad news to people like me? Well, as I just mentioned, Arecibo transmits 1 million watts. The typical conventional television transmitter, as you find on Sutro Tower in San Francisco, transmits about 3 million watts. In fact, there's 30 million watts of power comes out of the Sutro Tower in the form of television programs. That is the main sign of our existence. But what comes out of one of these? It's beamed carefully down on the Earth. Here's the actual parameters, and if you look about halfway down, you'll see the KU band payload. That's actually the channels that are providing the signal to the little dishes. Many of you have the 18-inch dishes. And what's the power? 75 watts. And not much less than 1 million watts or 3 million watts. You see some others are 20 watts. And that's all it takes to send a signal from 22,000 miles above the Earth to a little 18-inch dish on your back porch or whatever and give you a very fine television picture. It's one of the most amazing developments in the history of technology. Not only that, this is the pattern of the radiation as it's directed on the Earth from the satellite. You can see they actually are capable of tailoring it so it matches the contours of the places where the people are that pay the bill for the signal. It matches the continental United States. You see a little finger reaching out to Puerto Rico, another one to Hawaii. And this is brilliant engineering. But for us, very bad news, because not only is it only 75 watts, but almost all of that falls on the Earth and is absorbed. The actual power going out into space is probably not more than 10 watts. And that's a lot less than 1 million. If this becomes the way to transmit television, the Earth will become much harder to find. But we search. Another thing is the cell phones. Affordable even by poor people all over the world. And they radiate a power of only a few watts. And yet they work. We don't need high power to make that work. Again, a step in the development of our civilization leading to less visibility. So what this says is, well, we don't know what L is. We can only guess. We might guess there are other things which will keep L a large number for a long time, but we don't know what those are. I'll show you a couple of examples possible examples in a minute. But that allows us now to take a look, finally, at where we stand today. Now, this is actually a page that I did not invent. It's actually from the notes for a course at the Pennsylvania State University. I just picked it because it's an unbiased estimate of all the factors in the equation. You can see them here. Mean rate of stars, 1 to 10 a year. Fraction of stars, 0.1 to 0.5. I mentioned 0.5. Number of Earth-like worlds, 1 to 3. That's about what I said. Fraction of those where life develops from 0.1 to 1. I said it was about 1. Intelligence, somewhere between 1% and 1. So on. The lifetime here estimated at much more than our experience, 10,000 to 1 million. Well, if you multiply these all together, what do you get? Well, I want to show you an abbreviated version of this. If you take the most likely numbers for the first 6 factors, they all multiply together very conveniently to a number close to 1. And this makes it easy to abbreviate this equation into something much easier to remember. You can even put it on a California license plate if you want. mystify all your neighbors. What does that mean? N equals L. It's telling us that as best we can guess, and guess is the right word to use, the number of detectable civilizations is equal to that longevity, the length of time on average they stay visible. Now you may wonder why this is written in such fancy letters, and the scientists here know the answer to that. It's then when you don't really know something well in science, it makes it more believable if it's written in fancy letters. So N equals L. Well, what is L? We don't know. And unfortunately, people keep coming up to me and asking me, when are you going to succeed? When are you going to succeed? And I used to say by the turn of the century, but that was about 10 years before the turn of the century, and I found out that was embarrassing because pretty soon the turn of the century was there and we hadn't succeeded. So the right answer to this question is, in order to know how soon we will succeed, we need to know the value of L, but to know the value of L, we have to have succeeded. And if you say that real fast, it sounds sensible. But if that is not satisfactory to the questioner, and they say, wait a minute, so, okay, what is L? When are you going to succeed? Then the fallback answer, the desperation answer is soon. Now, soon is not very well defined scientifically, so you weasel out of it in that way. Don't ask me what soon is, but soon is the answer to that question, in case any of you are tempted to ask me that. Well, what should we search for? I've mentioned that we've been searching for radio waves. We could search for the lights of cities at night. This is a mosaic of photographs of the Earth at night taken from satellites in space. You can see the northern lights up there in the upper left-hand side. Over on the far right, the brightest country is Japan. Any of you who've been there know that they love to put all kinds of bright lights on their buildings at night. You see some strange things, some lights in northern Siberia, which are the waste gas from the oil fields being burnt at night. Same thing in Saudi Arabia. Here's the United States at night. If you've got good eyes, maybe you can find your house. I think you can probably find the Bay Area there, and you can see, in fact, Route 80 stretching from the Bay Area to Sacramento. And you can see Route 5 going all the way up to Portland and Seattle with little cities looking like beads on a string along the way. Well, it turns out it would take an optical telescope about 5 miles in diameter to see the lights of cities at night. So we're not going to do that now, but it's possible other civilizations do, and they know all about us because they have been able to build such large telescopes in space, undoubtedly. Or they have used their own star as a gravitational lens to make a giant telescope. You can do that. It makes a telescope with a lens equivalent to the diameter of the star, about 1 million miles. So it's a very powerful instrument. You can actually resolve cities on the planets of stars 100 or so light years away. And you might ask, why aren't we doing that? And the reason is the focus of the lens, if it's a star like the sun, is about 500 astronomical units from the star, which is about 10 times the distance to Pluto. So it's not doable by us yet, but it's in our future. And it could well be that this is the standard way to detect and study civilizations. You use the stars as gravitational lenses. Radio, this is what we used in the first search in 1960. It was an 85-foot telescope at Green Bank. Here's the equipment. Not a transistor or computer to be found. It was 44 years ago. But for those of you who are old enough, you will recognize over there on the right side a Wollensak tape recorder, which we had attached to the equipment so that we could record the voices of the extraterrestrials when we captured them with our big radio telescope. This monitored one channel at a time. It was used to search for signals from the 2 stars nearest to the sun that are like the sun, Tau Ceti and Epsilon Eridani, for 2 months. No signals from those stars were heard. Signals were heard, but they were from us.